Welcome back to the deep dive. Our mission today is all about acceleration. We are unpacking a massive keynote from CES. But this wasn't about shiny new gadgets. It was really a blueprint for the entire future of AI and computing.
And if you're listening, you should probably prepare yourself.
Uh-huh.
The central claim here is, well, it's stunning in its scale.
Mm-hmm.
We're used to platform shifts, mainframe to PC to the internet, happening once every decade or so.
Right.
But according to these sources, the entire computer industry is going through two simultaneous platform shifts right now.
Two at once. That immediately grabs your attention. So what are they?
Well, one is the one we all see.
Yeah.
AI applications are being built on AI. The intelligence itself is the new platform. And the second is the shift to accelerated computing, which fundamentally changes the physical hardware that software runs on. They call it a complete reinvention of the stack.
That sounds aggressive, but the investment figures they use to back that up are just staggering.
Yeah, they are. The presenter cited that roughly $10 trillion worth of computing capacity built over the last decade now has to be modernized for this new model.
Hold on, 10 trillion. That sounds like hyperbole. Is that just for AI gear, or is that global?
It's the total cost of modernization needed to run these new workloads efficiently. And to show you how seriously industry is taking this, they pointed out that R&D budgets across, get this, $100 trillion of industry are shifting focus.
Away from classical methods.
Completely.
Yeah.
And entirely toward these new AI methods. That's where the capital is flowing now.
And this leads to the most fundamental change, really, in how we interact with machines. The core idea is flipping. You no longer program software, you train it.
Mm-hmm.
It runs on GPUs, not CPUs. And applications aren't using pre-compiled code. They generate every single pixel, every token from scratch based on context. It's a living system.
And it's the speed of all this that is just so remarkable. I mean, if you look at the AI timeline they laid out, you see how fast things are accelerating.
Right.
So back in 2015, we had the first major language model, BERT. Then 2017, the transformer architecture comes along.
And it still took 5 years from that to get to the 2022 ChatGPT moment. That was the big global awakening. But then everything just sped up.
Exactly. Just a year later, 2023, we see the first reasoning models, which brought this concept of test time scaling, or TSS.
And that's the critical part, right? That's the compute-intensive step where the AI actually, thinks and reasons and checks its work in real time before it replies.
Yes, and that ability to think leads us directly to the big shift of 2024 and 2025, the rise of agentic systems.
And these are not just advanced chatbots. They're self-directed entities.
They're models designed to reason, to look up information, to use external tools, plan ahead, and even simulate future outcomes. They're becoming expert collaborators.
The keynote highlighted an agent called Cursor, which NVIDIA uses internally for software programming. That's a perfect example. The application layer is just dissolving. The platform is the intelligence.
And to operate at this level, these modern AI systems need a very specific structure. They have to be multimodal.
Meaning they understand everything.
Everything. Text, speech, images, video, 3D graphics, even complex stuff like protein structures.
Yeah, and they also have to be multi-model. They can't just rely on one big brain. They need to call on specialized models for different tasks.
Right. They cited Perplexity as a great early example of an architecture that uses multiple models at the same time in one reasoning chain.
And finally, they have to be ready for multi-cloud and hybrid cloud. You need that intelligence wherever your data is, right? On the edge, in your enterprise.
Exactly. And this architecture, it also solves that huge early concern everyone had, hallucination.
Ah, all right.
Because these systems use reasoning and reinforcement learning, these chain of thought techniques. They don't just guess.
They break the problem down.
Yeah, into known steps. The agent does research. It grounds its answer in truth before it ever replies. You teach it how to reason, not just to know everything from day one.
And that has just fostered this incredible wave of open innovation. We're seeing open models like DeepSeek R1, which is the first open reasoning system.
Yeah, and while they still trail the absolute frontier models by maybe 6 months, that gap is closing at an astonishing pace.
The result is this explosion in downloads. Startups, researchers, big companies. And what's interesting is that NVIDIA, even though they're a frontier model builder, is working completely in the open.
In really specialized domains, too. They're not just talking about language. They're building foundation models for digital biology tools like Lapertina, OpenFold 3.
Or for weather in physics like Earth 2 and ForecastNet. and even robotics with that group model.
And the crucial part here is building trust. They open source the models and the training data. You can actually look under the hood and see how it was trained.
Which is vital. And that transparency enables this new architecture we were talking about. You get an AI that's both highly customizable,
So it knows your private data, your company's secret skills.
while at the same time always being at the frontier, using the world's best intelligence from the cloud.
And the piece that glues it all together is the intent-based model router, the smart router,
The traffic cop.
the ultimate traffic cop for your AI.
Yeah.
It intercepts your request, figures out what you really want, and sends that prompt to the best model for the job.
Whether that's a huge external API or a secure local model.
And they walk through a perfect example, building a personal assistant on a local machine, a DGX Spark.
So the assistant uses a frontier model API for general knowledge, but
But it also runs a local open model right there on the Spark for your private stuff, like processing sensitive emails or internal documents.
so the router decides. If I ask for the capital France, it picks the big API.
Right.
If I ask, summarize that client email from yesterday, it stays local.
And because these are reasoning systems, they can interact with the physical world. The demo showed it hooked up to a little robot, controlling its behavior using third-party APIs for voice.
That potato off the couch example was kind of funny, but it's actually the most stunning takeaway. It shows the difference between code and real contextual understanding.
Absolutely. The agent managed complex, dynamic tasks. To-do lists, architectural rendering, telling a robot what to do. It was seamless. That's not science fiction anymore.
And that same agentic system is becoming the new UI for massive enterprise platform. We're talking Palantir, ServiceNow, Snowflake, CrowdStrike.
The command line is out. Talking to an intelligent agent is in.
So, moving beyond the purely digital world, we hit the next major inflection point, physical AI.
This is all about teaching computers the common sense of the physical world. Things we just take for granted.
Like what?
Object permanence, causality, friction, inertia. The basic laws of nature.
Which are a complete mystery to an AI unless we teach it. And teaching it means you have to be able to simulate outcomes.
You got it. An AI can't evaluate its plans if it can't simulate how the world will react to those plans.
And that's where the three-computer system for physical AI comes in.
Exactly. So think about an AI learning to drive a car. You have 3 stages, each needing different kinds of compute.
Okay, break that down for me.
You've got one computer for training. That's the classroom where the AI learns the rules.
Got it.
You have one for inference. That's the computer at the edge in the car's brain. That's the driver's license test.
And then the third one, the simulation computer. That's like the crash test dummy lab, right? Where it can practice a million weird scenarios safely.
That's it. Simulation is the heart of the system.
The big hurdle here, as always, is data. Specifically, ground truth data for physics. The solution seems to be synthetic data generation.
You're turning compute power directly into data. And that data is conditioned by the laws of physics.
Which brings us to Cosmos.
Right. Cosmos is described as an open frontier world foundation model. It's not for language. It's for the world itself.
So it's been pre-trained on internet videos, driving data, 3D simulation data.
And you can feed it something basic, like the wireframe output of a traffic simulator. And Cosmos generates physically plausible surround video from it. It uses compute to create scenarios the AI has never seen.
And the most immediate, highest stakes application of this is obviously autonomous vehicles. We're seeing Alpamo described as the world's first thinking and reasoning AV AI.
And it's trained end-to-end, camera in to actuation out, using human demonstrations and all that Cosmos-generated synthetic data.
The reasoning part is so important for driving, especially for that long tail of weird, unpredictable scenarios that cause accidents.
It's everything. Alpamo doesn't just react. It reasons about its plan, why it's making that plan, and the trajectory. It breaks down unpredictable situations into smaller, normal ones it knows how to handle.
And this isn't some far-off R&D project. It's deploying now. The Mercedes-Benz CLA is the first car with this full stack, launching this year, and they're calling it the world's safest car.
That kind of safety rating requires serious redundancy. The car actually runs 2 full AV software stacks at the same time. Yeah. The sophisticated Alpamo stack and a simpler, fully traceable classical AV stack. A safety monitor watches both and defaults to the simple safe system if Alpamo ever shows a lack of confidence.
Wow. And this goes way beyond cars, right? The same principles apply to the Industrial Revolution. Future factories are being thought of as gigantic robots.
And NVIDIA is integrating its full stack, the hardware, the AI, Omniverse, into the big industrial design players, Cadence, Synopsys, Siemens.
Which means future chips and systems will be designed by agentic chip designers inside a digital twin, a simulation, before a single physical prototype ever gets
It
made.
just massively compresses the whole design cycle.
So speaking of chips, we have to pivot to the fundamental problem underneath all this. Models are going 10x per year, test time scaling is generating 5x more tokens.
But Moore's law has slowed way down.
Exactly. Transistor increases are only around 1.6x a year. You can't meet 10x demand with 1.6x improvement.
So to get ahead of that curve, they had to embrace extreme co-design. For the Vera Rubin platform, they had to redesign 6 different chips all at once across the entire system just to get the performance leap they needed.
And the sources confirm Vera Rubin is now in full production. So let's talk numbers. The Vera CPU, it's custom, designed for performance per watt.
It delivers 2 times the performance of the last gen, 88 physical cores with spatial multi-threading.
But the real star is the Rubin GPU. It gets 5 times the floating performance of the previous generation, Blackwell.
And here's the crazy part. It only has 1.6 times the transistors. The takeaway isn't just more transistors, it's the cleverness they used to squeeze that performance out.
And that cleverness is this thing called the MV-FP4 Tensor Core. For the listener, why is dynamically adjusting precision so revolutionary?
Okay, think of the processor like a calculator. Usually you set how many decimal points you need your precision before you start. If you need hyper-accuracy, you use 64-bit, but that's slow. The MV-FP4 Tensor Core figures out how to dynamically change the calculator setting while it's working to maximize speed. It keeps the high precision only where it's absolutely necessary. It's how you get 5x performance without waiting for Moore's law.
That's a phenomenal achievement. And the efficiency gains are just as important. The new MGX chassis that holds all this is 80% liquid-cooled.
Using 45 degrees Celsius water, which means you don't need expensive water chillers in the data center. They estimated that could save 6% of the world's data center power.
It's system-level innovation. And they reinvented networking, too. The NVLink 6 switch moves data at 240 terabytes per second.
Which is, what, twice the bandwidth of the entire global internet?
Yes, just to make sure every GPU can talk to every other GPU instantly.
And this solves the big working memory problem. AIs need huge amounts of context, like having 100 browser tabs open. If the AI has to go off-rack to get that context, it just grinds to a halt.
Which brings us to this new memory category.
Exactly. The Bluefield 4 DPU is managing security, but it's also creating a new storage category, the Dynamo KV cache. It provides an extra 16 terabytes of fast memory per GPU right there on the rack. It basically glues that working memory directly to the processors.
So when you put this entire redesigned system together, the CPUs, the Rubin GPU, the cooling, the fast memory, what's the bottom line? What's the performance impact for the listener?
Compared to the last generation, Vera Rubin needs only 1/4 of the systems to train a projected 10 trillion parameter model. It delivers 10 times higher factory throughput per watt, and it slashes the token cost by 1/10.
That is a generational leap, achieved through sheer architectural brilliance.
It really is.
So when you look at the whole stack, from the new Vera Rubin chips to the Cosmos World model to the Agentic systems on top, the theme is clear. AI isn't just an application anymore.
It is the platform. And all future applications will be built on it, which require this complete reinvention.
And for you, the listener, this means the tools are here right now to create these highly customized, domain-specific AIs, like that private email agent.
While you're still leveraging the power of these massive frontier models, customization and the frontier are no longer mutually exclusive.
So if we connect this back to the bigger picture, it raises a really important question. The entire stack, from the code on a Vera Rubin supercomputer to the logic controlling the physical world with Alpamo, it's all defined by reasoning and synthesis now, not pre-programmed rules.
So what happens when the majority of industrial design and manufacturing, including the design of future chips themselves, is guided, optimized, and verified entirely by these agentic AI systems inside a digital twin before a single physical prototype is ever commissioned?
That's the next industrial revolution.